So we'll now look further in Module 4 into using this procedure, this procedure for generating random paths and random stocks prices. We'll use it now to value options. And we've already seen quite a bit of this, so I'll just a quick review in the notation of this section in the chapter. So V is an option that has a payoff at time t. It's a general European payoff. And by that I mean it could be a put, could be a call, could be a forward contract. It could be any kind of a financial derivative security, exercisable at time little t, and it has an explicit payoff function at that time. That's all we're assuming. So the Monte Carlo price at time 0 is given by this usual, I generate a random sampling of little n prices, and this little n is just notation. It's not related to the little n in our lattice generally. So this is a general procedure. Just imagine I generate little n prices at expiry. I plug them into the payoff function, and I average those payoffs and I discount. And when I generate these prices, I'm certainly going to generate them in the risk neutral. I keep emphasizing that, and that should be quite familiar. And it doesn't matter whether I'm assuming those stock prices are the binomial distributions of Chapter 10 or 11, or whether they're the log normal distributions, which the binomials converge to. The point is, in either case, you don't use alpha, you use R for the risk neutral. So in a call option, we have an explicit formula, as we would for a put, as we would for any kind of an explicit European. So as an example, we might value a 3-month European call. So we'll start with a stock price of 40. It's an at-the-money call, so we'll have a strike of 40, 8% risk-free rate, no dividends, and 30% volatility. We're going to use a single step in this model. So H is 0.25. Everything's measured in years, so we're going to take only one step. So our formula for stock prices at time 1/4 of a year as a function of stock price at time 0, you can see all the parameters. The 8% risk-free rate, after all, this is an option valuation. We use R. Subtract half the variance. H is 0.25. Then we have the vol times square root of the time, and we have this Z. So here's an example of where we're only going to take one step because it's a simple call option, and therefore we don't need the intermediate stock prices. We just jump right to expiry with a single step. So here you can see the author is proposing generate 2,500 values. And again, this is easy to do in Excel. You could just well imagine using the RAND function, the norm S inverse function, generating 2,500 normal variates, and substitute each one of those 2,500 Z's into this formula, producing 2,500 stock prices. You could then value the option at each one of those 2,500 stock prices. We then need to average. That's our way of taking an expectation. We're trying to find the average payoff. And then finally, we need a discount rate. And we get in the sample that the author did. And of course, there'll be estimation error. If you repeated this exercise yourself with 2,500, you would probably get a price different than 2.804. And one can do statistics, we'll talk about that in a minute, to see how much error or a variability might there be in this estimate. But you can see in this example it's a pretty good approximation. And that's my experience, that when you're dealing with several thousand, 2,000, 3,000 for a simple put option or call option, you get quite close to the theoretical Black-Scholes price. If you repeated this calculation with only a sample of 100 or a couple of hundred, you would notice larger errors. not surprisingly, because after all, we're trying to estimate the mean of a distribution, and we don't expect a terribly accurate estimation if we only sample lightly.